Hello and welcome back to this new video about radio meteors. My name is Stijn Calders and today I will talk about a citizen science project called the Radio Meteor Zoo. Hopefully by the end of this video you want to join this project. In a previous video we explained that the BRAMS Network consists of one transmitter in Durbe, which is a small village in the south of Belgium, and about 25 receiving stations installed all over the country. Most of them are hosted at public observatories, schools, and other organizations that are active in public outreach. Each of these stations saves the signal from the receiver in a sound file of 5 minutes. In this way, one station generates 288 recordings per day. That means that for the whole network, we collect more than 7,000 recordings per day. That is a lot of observations to process. Luckily, we get help from an automatic detection algorithm. These algorithms usually detect between 1,500 and 2,000 meteor echoes per day for each station. However, during meteor showers, the particles that enter the Earth's atmosphere are much bigger. Because of this, the meteor echoes are more complex than during normal days. I have put some examples of spectrograms with striking examples on this slide. These blobs are all meteors. Unfortunately, the automatic detection algorithm failed to detect many of these echoes. Here, the human eye remains the best detector. But how do we deal with such vast amounts of observations? That's where you, the citizen scientist, come into the picture. In the Radio Meteor Zoo, you have to draw a rectangle around everything you consider to be a meteor. The first time that you do this, a tutorial will guide you what to look for. If you are still in doubt, you can ask questions about an image in the talk section. So plenty of ways to train yourself to become a professional meteor hunter. With these results, we do two things. First, we use it to assess the activity during meteor showers. And secondly, we use your data to train a machine learning algorithm to detect meteors the same way as we are doing. Don't be afraid to make errors. Each image is processed by 10 different volunteers, and we consider only those regions of the image to be a meteor if at least half of these volunteers have selected it. So in the example above, the red rectangles are the individual classifications, while the green ones are the aggregated results. In mid-August, we can observe the most well-known meteor shower, called the Perseids. This is an example of the results that we obtained from the Radio Meteor Zoo. The red curves are the total number of meteors that you have classified. However, this is a combination of both shower meteors and sporadic ones. The black sign is an estimate of the sporadic activity. So if we subtract this sporadic activity from the total number of meteors, we obtain a blue curve. This is the number of observed shower meteors. The blue curve must also be corrected for the position of the radiant. As you probably remember, the radiant is the apparent point from which all shower meteors seem to originate. The radiant elevation is indicated with the green circles in the bottom panel. As you can see, the observed shower activity is low when the radiant elevation is either low or very high. However, the actual activity might be constant. To correct this, we will have to apply a correction factor called the observability function. At the time that this video was recorded, this was still work in progress. The citizen scientists of the Radio Meteor Zoo have processed the Perseid activity during several years. Here you see the peak activity of the shower falls each year in the morning of the 13th of August. This is as expected. In one of the previous videos, my colleague Hervé explained that when a comet comes close to the Sun, it will form a tail of dust. In the case of the Perseids, it's a comet Swift-Tuttle. As you can see in this video, the dust trail of this comet crosses the Earth's orbit, and the Earth passes that point at the same moment every year. We see also that in 2017 there was a lot of activity the day before. The reason might be that the Earth crossed two different dust trails from this comet. It is interesting to study this in more detail and to compare our radio data with visual or camera observations. This concludes the video about the Radio Meteor Zoo. If you want to know more, you can read the links that we will post below this video. In the next video, my colleague Hervé will talk about the specific objectives of the BRAMS project. Thank you very much, and we welcome you at our Citizen Science project at the website that is shown on this slide.